let's say we are given a square that is resting on two surfaces, propped up against two surfaces. All right, we're going to act upon the square with a force P. The square has a 100-pound weight, and each side of the square is 6 inches. 6 inches, 6 inches, 6 inches, 6 inches. The coefficient of static friction for all surfaces, mu s, is equal to 0.5. Find the magnitude of force P where motion impends. Okay, so this is tipping in that we have distances where it rotates, and then it's slipping because we've got the wall friction that's holding it into place. So this is kind of a twofer. All right, I am going to begin with a free body diagram. All right, and this is acting through the center here at 100 pounds. Again, assuming one continuous material, continuous thickness, homogeneous and isentropic. Woo, that was tough. Okay, so thinking about, I'm going to call this point over here A and this one over here B. So thinking about point A, if I'm rotating P clockwise, that means that it's going to want to react counterclockwise. So we have a friction at A, and then we have a normal at A. Okay, same thing down here at B. It's going to be wanting to act counterclockwise for impending motion. All right? So there's all my forces. Okay, so let's use equilibrium, summing forces in the x direction. I have P minus normal A plus friction B, right? Summing for forces in the y direction, I have minus 100 plus friction A plus normal B. I'm going to sum moments about B. Counterclockwise is added to the equation. B is down here at the bottom. So 0 is equal to, all right, if this is 6 inches, that means this distance is 6 divided by the square root of 2 inches, as is this, and as is this. All right, so that means we're going to have friction A times 6 divided by the square root of 2 inches, going counterclockwise, plus normal at A times 6 divided by the square root of 2, and then minus P times 12 divided by the square root of 2. And then friction B and normal B pass through B. All right, 5 unknowns, 3 equations. But is it really? Okay, motion in pins, which means friction A and friction B are at a friction max, right? So therefore, friction A is equal to 0.5 normal A, and friction B is equal to 0.5 normal B, okay? So they're at a maximum, but they're still dependent on their normal forces, which shouldn't be the same, okay? Because pushing down on the ground is different than pushing to the right on the wall. However, that does reduce our number of unknowns. You are now 0.5 normal B, and you are now 0.5 normal A, and you are also 0.5 normal A. Now I have 3 unknowns and 3 equations, and solving simultaneous equations, I find that P is equal to 75 pounds, and for the record, normal A is equal to 100 pounds, and normal B is equal to 50 pounds.